So now we will have the third final talk for this session, a compositional methodology to harden program against multi-fault attacks, but Etienne Boespflug, sorry, from University of Grenoble.
So hello everyone, I'm Etienne Boespflug. I will present compositional methodology to harden program against multi-fault attacks, and it is joint work with Laurent Mounier, Marie-Laure Coté, and Abderrahman Boukar. Thank you. So at first, let's take a look on this example from the FIS collection benchmark, in which you have the verify pin function that will verify the try counter, and if he remains some try, we will call the compare function, and we will consider especially the software level. So the test inversion model, for instance, allow the attacker to invert the branch that is taken during a conditional branching. And you have an example of fault at line 6 that allow the attacker to completely skip the loop and return true for the comparison. So software countermeasures are usually program transformations that can be placed. And you have another example, line 9, where we verify the loop counter. And if the loop has not been run exactly size time, we will stop the card. So when we consider multi-fault, the countermeasures themselves can be attacked. And here you have another example of the second fault, line 9, that will skip the countermeasure and then make the attack successful. We use the tool Lazard that is developed at Verimag and is an LLVM level robustness tool using dynamic symbolic execution with the tool CLI, and using two main fault models, test inversion that has been explained previously, and data mutation on the load instruction, meaning that we can inject an arbitrary value during the load instruction. You have here an example of different version of verify pin from the FIS collection, and I will not enter in the detail of the metric of comparison, but you can see that comparing different versions of program is difficult. Moreover, using dynamic symbolic execution, because the attack traces can match to several concrete attack traces. And you can see here, for instance, that verify pin 4 is less robust than verify pin 5 that has no one-fault attacks. But for instance, comparing verify pin 3 and verify pin 4 is more difficult. So multi-fault are state of the art. We have some example of attacks that combine several faults to achieve their goal. For instance, the Wookiee project at the STIC 2020. And the standard try and error approach, meaning that I have an attack, I will place a countermeasure and verify that the attack is removed, is not applied in multi-fault because the countermeasures themselves can be attacked, and it's pretty unrealistic to test on possibility of countermeasure placement on the program and running a robustness analysis on each variation. Moreover, several tools use the systematic approach, meaning that we will place countermeasure on all the program or all sensitive parts of the program that are chosen by the developer. And moreover, this kind of approach can lead to unnecessary protection. So the problem in this presentation will be how to help the developer to place countermeasures, especially at software level, and give some guarantees of the program generated in multi-fault context. So our goal is to place countermeasure against multi-fault attacks, meaning that we will consider a set of fault model using a combination of several faults of those fault model. We will target robustness in N faults, and we will use a catalog of countermeasures that are applied on an injection point of a specific fault model that we call injection point granularity. The approach is compositional because we will first use the analysis in isolation to give some property of the countermeasure in multifault on the protection scheme, and later some placement algorithm will use those properties to apply a protection on each IP in the program. And we will use a set of attacks on the original program with respect to the set of fault model M. So at first, let's take a look at the analysis in isolation. The basic idea is to give an analysis reusable outside of any program context on the protection scheme, meaning that, yes. So in single fault, we will consider adequacy, which corresponds simply that the fact the protection scheme actually blocks the attack in one fault. And considering multi-fault, we will research the vulnerability level, which corresponds to the minimal number of faults that the attacker has to spend to introduce an abnormal behavior of the IP. So by definition, a non-protected injection point has a vulnerability level of 1. One fault is recurrent, sorry. And it can be computed with laser or other robustness analysis tool, as we will see. So here you have an example of branch duplication scheme that is applied on the LLVM level. You have here the unprotected IP that is basically a branch instruction branching on a basic block, and the duplication that will duplicate the branching instruction and go into a countermeasure block, stopping the card in case of incorrect behavior. So as we search the minimal number of faults we can to produce an abnormal behavior, we will have to define two important parts. The nominal behavior of the countermeasure that will require to identify the input and the output of the scheme. So in our case, the input is the conditional LLVM temporary cond that is used by the branching instruction. And the output of the scheme is the destination branch. The entry point is the branching instruction. The output point is the destination block, or the stop of the card, that is another output point. And the nominal behavior of this IP is to reach BB true if and only if the condition is true. And it will correspond to the post condition to be verified during analysis in isolation. And because we are in multi-fault, we will also have to take into account the attack surface. In our case, we have the original IP1, the original IP1 that is still here in the protection scheme, and the injection point introduced by the countermeasure, in our case, IP1T. So here you have also the tripling, an extension of the test duplication, and the isolation analysis with the tool laser gives the following result. The unprotected IP has one fault attack, and the protected IP has a two fault attack, and the triplication scheme has a three fault attacks, meaning that we will have a vulnerability level of 1 for the unprotected IP and 2 and 3 for the true protection scheme. Because we are in multi-fault, we can combine some fault models. So here's an example of countermeasure targeting the load instruction and combining the data load and branch inversion fault model. And you have here the result, also the duplication of the vulnerability level of 2 and the triplication as a vulnerability level of 3. So in summary, the idea is to compute properties outside of context about the protection scheme. We will especially consider the vulnerability level for multi-fault. And we have two countermeasures, branch multiplication and load multiplication. This is an error that have the vulnerability level equals to 1 plus n, being the level of duplication of the countermeasure. And this vulnerability level will be used by the placement algorithm to select which IP will be protected at which level. So now for the placement algorithm, we will generate a PayPrim program which is robust to n fault from the set of fault model M. And the basic structure will be the same for all algorithms. Obtain a set of attack traces for the original program P using all fault model in M and a user-defined attack objective. Compute the required vulnerability level for each IP. This is this part that will change depending on the placement. And the third part will be simply to generate the protected program with the required vulnerability level. And I will present you three approaches: the systematic placement, the block placement, and the distributed placement. So at first, the systematic placement algorithm are three. We have the naive algorithm, which correspond to what is done by systematic placement tool. It does not require any attack trace and will simply protect all IP in the program with a vulnerability level of n, of at least n, meaning that no IP can be violated with less than n+1 fault. The attack placement algorithm use the set of attack traces on the original program P and will protect only IP that intervene in the successful attack on P. So we will require that A is representative, meaning that we have all sequence of successful fault in our traces. And I will not explain more the minimal variant that use a subset of the attack traces. Then you have the block placement algorithm, for which the idea is to protect only one IP per attack traces, or at least one IP, with a vulnerability level greater than n. And this algorithm is heuristic based because we will start with lower fault count traces and we will protect the IP that has the most occurrence during the set of attack. Why does it work? Because of the compositional approach, we have at first encapsulated all the additional behavior introduced by the multi-fault attack inside the injection point or the protected injection point. So we have the guaranteed, for instance, that this protected IP would require 2 faults for the attacker to produce an abnormal behavior. And the exploration of the attack traces on the original program give us some information about which IP can lead to a successful attack. And for instance, we can see here that if IPC is not protected, we will have a successful attack in one fault. But if IPA is not protected, we can instead protect IPB and still do not introduce new attacks. And thus, we can question if we can delay the protection on a trace, maybe we can distribute the protection among the trace. And this is the idea of the distributed placement that will actually distribute the protection with different vulnerability level among the traces. So you have here a figure showing different attack traces, and for each attack, we can get a constraint on the vulnerability level on the program. For instance, on the trace E, we have 2 faults on the IP A and 1 fault on the IP B, meaning that to be secure on N fault, we should have 2 vulnerability level of A, called XA, plus 1 vulnerability level of B should be greater than N. And generating all the constraints for all the fault trace of the program give us an integrally linear programming problem in which we will try to minimize the sum of the protection applied on the program. So this will give us the optimal placement on the program to achieve a robustness in end fault. It will also require an additional condition because we want to be sure that the fault model used to generate the trace is at least more general than the one used by isolation analysis. So we have made some experimentation for the different algorithms. You have here the column indicating which algorithm is used. Here it's for the verify pin program using branch inversion and thus branch multiplication countermeasure. We have a total of 8 injection points in the program, and here you have the sum of the protection, so the sum of the vulnerability level of all the IP in the program generated by the placement algorithm. So as you can see, in one fault, we will protect all the IP for the naive, but if we have the attack trace set, we will have to protect only 3 IP. And the block placement approach is optimal starting to 2 fault. Here you have the result for another example, memcompare secure version 3 that use a combination of test inversion and data load mutation fault models, and the combination of the corresponding countermeasure. And here you can see that actually the program has only 1 attack in 4 faults. That's why all the algorithm does not protect anything before the 4 faults. And the block placement will protect 1 IP with vulnerability level of 4. And then the optimal algorithm is able to protect only 1 IP because the 4 fault attacks is in fact 4 fault on the same IP. So the trace is secure by simply doubling the test. And using a combination of data load and branch inversion, we have also the optimal algorithm that is the only one to be optimal. And the last experimentation that I will present here is the firmware updater that simulates the update of a firmware from a remote source. It uses also a combination of the 2 fault models. And as you can see, the optimal placement is optimal for the branch inversion fault model, but for data load, the minimal placement is enough to ensure an optimal placement. So in conclusion, the robustness of the placement depends on the property of the catalog. We will require to have a countermeasure that have the required vulnerability level to be able to protect the program. And the protected program is guaranteed to be robust on end fault if we have the required protection level, vulnerability level, sorry. And if not, we will be able to know the attack traces on the protected programs that will remain. And if the attack trace set in entry is incomplete, meaning that there is an attack, but we don't have it in our set of attack, we can say that we are at least more robust because we will have protect some injection points and maybe not some attacks. So as expected, the distributed approach is always better than the block approach that is better than the systematic. And the optimality of the placement is guaranteed by the integral linear problem. In terms of performance, the complexity of all algorithms correspond only to pass on all attack trace of the program, except for the optimal algorithms that is in theory NP complete, but in fact the 1 fault attack puts strong constraint on the problem, and in our experimentation the exploration of the attack trace was by far the more expensive, so the dynamic symbolic execution with laser. So in future works, in conclusion, we have the isolation analysis that is that allow to reason about unprotected and protected injection point outside of the context of any program, and the vulnerability level specifically quantifies the guarantees of the countermeasure with respect to a set of fault model. And the different placement algorithm gives strong guarantees of robustness, even if the trace set is incomplete, and the optimality is guaranteed by the ILP problem. So in future works, we would like to study some countermeasures that are propagating states, because in our example, it was not the case. All application is completely independent, and this could require to consider two isolation analysis, one where the internal states are sane, and one of where the internal states are corrected. And another difficult question is the study of more complex control flow fault model, because isolation analysis require to be isolated, it's a name. So if you have, for instance, fault models that allow to jump in the middle of a protection scheme, the methodology is not applied. And moreover, the methodology has been done on LLVM level because we are using the tool laser, but in theory, there is no particular reason to be not able to use it on other representation level, but it may be some difficulty depending on the objective attack that is used. And before I conclude this presentation, I would like to talk about model protectability. We have shown that we have programs that are locally protectable, for instance, test inversion and branch and data load, meaning that it exists a countermeasure that have a vulnerability level greater than n for all n. And there are works, for instance, given Wilson, that shown that some models are not protectable at all. For instance, we can say a fault model that will be able to replace an entire program. We cannot do anything at the software level. So the question more theoretical is there some fault models that are not protectable with our approach, but protectable in the general case, for instance, with more complex program transformation? We think so. And is there some programs that are not protectable, but maybe we can make the attack more difficult for the attacker by diluting the attack inside the program? So thanks you for watching.